So we've begun our study of complex numbers in rectangular form. So look at this number right here. The 2 is the real part, and then the 6j is the imaginary part. What I'd like to do now is, because complex numbers have 2 parts, they can be represented as a vector quantity in the rectangular coordinate system. Doing this allows us to describe a complex number in another form, the rectangular form, called polar form. So this is where we're headed now. We're leaving rectangular form and going to what's called polar form. The polar form of a complex number can perform 2 of the 4 operations, multiplying and dividing, much more quickly. We can also raise complex numbers to a power, is what that says over there. Way easier, and take square roots and cube roots of them, etc. So the form is what's nice in order to multiply, divide, raise to a power, take roots, and I can even work with them to ultimately get to add and subtract, so the 4 operations. So we're just going to talk about a vector quantity, and we're going to define the rectangular coordinate system such that this is the real axis and the y-axis is the imaginary axis, and I'm just going to ask you to draw these as vectors. So this positive 2 plus 6j is asking us to go from the origin to the right 2 on the real axis and up 6 on the imaginary axis, and put a dot there and draw the vector from the origin to that ordered pair, and we're done. We've drawn the vector 2 plus 6j. We will get to the point where we will talk about the fact that it's formed by a right triangle where the legs are 2 and 6, and we'll find the hypotenuse, and then we'll find this angle. So we'll be using the Pythagorean theorem and tangent, the trig function tangent. But for now, let's graph these complex numbers. So this is a positive 4 on the real axis, and this is a minus 1j on the imaginary axis. So I'll go over 2, 3, 4, and down 1, and graph that complex number in the 4th quadrant, and make sure it's a vector, so make sure you put an arrowhead on it. Let's go ahead and do the next one. So what quadrant will that be in, where this is negative and this is negative? So I'm from the origin, I'm going to go left 2, because that's a negative 2, and down 5, and then I'm going to draw the vector from the origin to that ordered pair, and I've drawn a picture of this. Okay, so in order to start to understand why we can add vectors and subtract vectors, multiply and divide vectors, we're going to go ahead and add these 2 complex numbers that are in rectangular form graphically. So that's what we're going to do next. So I'm just going to draw each vector independently. So the first one is to the right 4 and down 3, and I will draw that vector and put the arrowheads on it. Then the next one is to the left 1 and down 2, and I will draw that vector and put the arrowheads on it. Now remember, I've already learned how to do this. I've already learned that a real 4 and a minus 1 combines to be a positive 3, and a minus 3j and a minus 2j combines to be a minus 5j. That's the answer to this problem. But what I want to do is I want to do it by vectors, by a sketch. And so I'm going to draw a line here that's parallel to this line, because we learned when we studied vectors in Math 118 that if you put their tails together and drew a parallel line opposite each vector, then the resultant, or the answer to your problem, would be from the origin to the opposite corner. So right there, that was supposed to be a straight line. And that's my answer. But really, this ordered pair is my answer here. So if I go from the origin to the right 3 and then down 5, I have this answer via a picture. Let's do the next one. So I want to go for the first one to the left 3 and up 4. And then the next one is to the left 5 and down 1. So I'm going to go to the left 1, 2, 3, 4, 5, and down 1, and draw that vector. Now this is hard because this is going to be off the graph paper. But let's just go find out what the answer is without graphic representation. So a negative 3 and a negative 5 totals to be a negative 8. And 4j positive minus 1j gives me 3j. So if I were to draw a line parallel to this one off of here, it's okay, I guess. And then if I draw a line parallel to this one off of this head of this vector, then the resultant is out here at this spot right here. And, you know, I'm going to try to estimate. So I went off, you know, one, you know, it's really 3 over from here because it's 1, 2, 3, 4, 5, 6, 7, 8 to go right here. And then this right here, it truly turned out to be up a positive 3j. If I want to subtract them, all I have to do is add the opposite. So you could either go, let's go with the first one, go to the right 5 and down 2. And, you know, when I want to subtract this one right here, I'm going to do in green because it's light. And actually, maybe I'll do it as a highlighter. So I'll go to the left 2 and down 4. And this would be the vector, but I want to subtract it. So I've got to have it head this way instead. When I subtract, I add the opposite. Or remember, whenever you subtract, you add the opposite of these. So this would become a positive 2 and a positive 4j. So this should, the vector I'm looking for is to go to the right 2 and up 4, and that's how I could graphically show that I'm going to find the solution to this. Now remember, I am going to take 5 and 2 and get 7. And this minus 2j and a positive 4j is a positive 2j. And my parallelogram should take me out to the right, a positive 7. So here's 5, 6, 7. And then up 2. Sure looks like I go to the right 7 and up 2 to get to that spot, which is the resultant of this. All right, graph the complex number and its conjugate. Describe the relative position. So let's just pick one. Let's pick the complex number 2 plus 3j. So I go to the right 2 and up 3, and I'd have a vector right here. Well, its conjugate is 2 minus 3j. So I'd go to the right 2 and down 3. So here's its conjugate. Let's do it again. All right, so it looks to me like they're reflective over the x-axis. Let's pick another one. So let's put a negative value for x, a negative 2 plus 3j. So there's our complex number we're going to work with. So I'd go to the left 2 and up 3, and I'd get this complex number. Its conjugate would be a negative 2. You don't change the real part, you just change the imaginary part. So you go to the left 2 and down 3. So because just the imaginary part gets changed, it absolutely reflects over the x-axis. Just kind of interesting. Not a big deal, but this conjugate thing is a very interesting topic, and in terms of multiplication in rectangular form, very, very useful, and division, excuse me.